Greetings, Mr. Sutton here with the BC Calculus Chapter 2 Quiz Review Number 3 solutions on continuity, intermediate value theorem, and slopes of tangent lines. For this problem, we're trying to find intervals of continuity for this graph. Let's begin by finding the discontinuities and leaving those out. So we see that we have a removable discontinuity here at -7 and at +1. We also have an infinite discontinuity, an asymptote, here at x equals -2. Since there are no endpoints, we can start at -infinity and go until this -7 removable discontinuity. Our next interval is going to be from -7 to that asymptote at -2, and then from -2 to +1, and then finally from +1 to +infinity. For this problem, we're trying to write intervals of continuity for this crazy-looking graph. Now, there's a whole bunch of discontinuities here. Let's start by noting the endpoints. So we have an endpoint at x equals -7, so everything to the left of that's an undefined area. So from -7 until, looks like we're going to +infinity over here. And now for other discontinuities, I'm going to start with the infinite discontinuities. So we've got an asymptote at x equals -4, and also another one over here at 3. We have some jumps going on. We have a jump at -2 and another one at 1. And we've also got some removable discontinuities. We've got one actually at the endpoint here at -7, and over here at 0, and also over here at x equals 5. So let's go through and write our intervals now. So we start at -7, rounded parentheses, because we're not including that as an endpoint. And actually, we wouldn't even need to put a bracket if it were solid. So we're going from -7 to -4, then from -4 to -2, and then from -2 to 0, 0 to 1, from 1 to 3, from 3 to 5, and from 5 to +infinity. For this problem, we're trying to find points and types of discontinuities for this f of x function. Since this is a polynomial, it has no discontinuities, so there are no points of discontinuity. For this problem, we're trying to find points and types of discontinuity for this weird-looking function. Now, if we look at the individual parts here, this first term is exponential, which is known to be continuous everywhere. The next part is a sine function, which is also known to be continuous. Since exponential and sine of x are both continuous, this whole function is continuous and has no points of discontinuity. We're trying to find points of discontinuity and their types for this problem here. Since this is a rational function, we have to look for things that are going to make the denominator 0. And to do that, it's also good to factor this so we can see if we have any common factors with this x minus 1 up here. So we've two things that multiply to -4 and add up to 3. That would be -1 and +4. And we see that these x minus 1s are going to cancel. So that means that x equals 1 has a removable discontinuity. And x equals -4, the 0 down there that we could not cancel out, that's going to be an asymptote, an infinite discontinuity. In order to prove continuity at a single point, like we're trying to do on this problem, we need to do three things. We need to show that the function exists at that point, that the limit exists at that point, and that the function value and the limit equal each other. So in practice, to do that, we end up trying to find the left side limit, the right side limit, and the function value. So let's start that on this problem. I'm going to start with my left side limit at 0. So that's going to be whatever I get when I plug 0 into this first function here, because this was for x values less than 0. So 3 minus 0 squared is 3. Next, I try the right side limit. So that's going to be plugging into this second rule here, which gives me a value of 2. Now, normally, I would go ahead and actually find the function value, which happens to be the same as the left side limit. It's 3. But I see that these limits are different, which tells me right away that the limit as x approaches 0 from both sides does not exist. Because the limit doesn't exist, that tells me my function is not continuous at x equals 0. To determine whether or not this function is continuous at x equals 0, I need to figure out the two-sided limit at x equals 0, the function value, and then I need to make sure that they both actually equal each other. So for the two-sided limit, this is kind of a weird setup for this function. Basically, whenever x does not equal 2, we use this rule here. So you could think of this rule as standing for x less than 2 and also x greater than 2. So to find the limit as x approaches 2, I basically need to plug into this rule where x does not equal 2. So we have the limit then as x approaches 2 of this rule here. And I've taken a moment to factor this. So x minus 2, x minus 3 in the numerator. Because in order to actually find this limit, I mean, if you just plug 2 in, you've got 0 over 0. So we need to cancel out these x minus 2's, leaving us with just the limit as x approaches 2 of x minus 3. And if I plug 2 into this, I get negative 1 for my limit. So my limit exists. I've verified that part of proving that I have continuity at x equals 2. Now I need to figure out f of 2 itself. And that's just whatever I get when I plug 2 into the function, which is, let's see, 2 minus 3 is going to be negative 1. To show that I have continuity at this point, I need to actually state that my limit of f of x as x approaches 2 and f of 2 equal each other. This tells me that first off, these two things exist, which is conditions 1 and 2 of continuity, and that they equal each other all in one shot. But to say that they existed, we needed to show all this stuff up here. All right, so since I have these two things equaling each other, I know that my function is continuous at x equals 2. For this problem, we're trying to find a value for this a in here that makes this function continuous. So in order to make the function continuous, we have to start by checking the left and right side limits and the function value at 3 with this a sort of hanging around. So our left side limit, that's going to be plugging 3 into x squared minus 1. So 3 squared minus 1, or 9 minus 1, which is 8. And now the right side limit and the function value, f of 3, are both going to involve plugging 3 into this rule here. So 2a times 3, which is 6a. So we know that the right side limit, the function value, and the left side limit all have to equal each other. So that means 6a and 8 must equal each other. Dividing both sides by 6, we can reduce that to 4/3 for our a value. For this problem, we're asking if the IVT, the intermediate value theorem, shows the existence of a c such that f of c equals 7 over the interval negative 2 to 3 for this quadratic function. So we always have to start by checking continuity. Since this is a polynomial, our function is continuous everywhere, including the interval from negative 2 to 3. So that means the IVT at least has a chance of applying. Now, in order for the intermediate value theorem to work, to guarantee that we can find a y value of 7 on this interval, we need to be continuous on the closed interval, and we also have to ensure that the beginning and ending y values, that the 7 is between those. So our first y value, what we get when we plug in negative 2 to our function, let's see, that's going to be 4 minus 10, so negative 6, minus another 4, so negative 10. And then we've got, let's see here, 3 plugged into this function. That's 9 plus 15 minus 4, so that's going to be 20. Is 7 between negative 10 and 20? It is. Therefore, the IVT guarantees that 7 exists as a y value for this function on this interval. For this next problem, we're trying to see if the IVT shows the existence of a c such that f of c equals 0 for this function on this interval. Now, with IVT, we have to ensure that the function is continuous on the interval in question. That way, we're guaranteed to run through all the y values from beginning to end. For this one, we notice that we have an infinite discontinuity at x equals 7. Since we have a discontinuity that's actually inside this interval from 6 to 12, that means that the IVT does not apply, and we can't go any further with this problem. For this problem, we're trying to show that the IVT guarantees f of c equals 0, so we have a y value of 0 for this function on the interval from x equals 0 to x equals 5. To make this happen, we first have to show that this function is continuous on the interval, the closed interval from 0 to 5. So this is an exponential function. It's a decaying exponential function for parts of it. So that means it's continuous everywhere, including 0 to 5. Next, we have to check to see that 0 is between the beginning and the ending y values, which means we have to find the endpoint y values. To do that, we're going to plug the endpoint x values of 0 and 5 into the function. So if I plug 0 in for x, I've got 1/2 to the negative 5. That's really 2 to the positive 5, or 32. Now if I plug 5 in for x, that's 1/2 to the 0 power, which is going to be just 1. Is 0, the y value we're looking for here, between 1 and 32? It is not. It just misses the cutoff. So since 0 is not between the endpoints, that means the IVT can't guarantee that we're going to find y value 0 on this interval. There still might be a y value of 0. We can't exclude it. However, we have no guarantees that we're actually going to find it. For this problem, we're given this function 2x squared plus 4, and we're trying to find an equation of a secant line through x equals negative 3 and x equals positive 4. So in order to get the equation of a secant line, we first need the average rate of change, because that gives us the slope of a secant line. So to get average rate of change, we need to do basically y2 minus y1 over x2 minus x1. So f of 4 minus f of negative 3 over 4 minus negative 3. F of 4, that's going to be, let's see, that's 16 times 2, so 32 plus 4 is 36. And then f of negative 3, that's 18 plus 4, or 22. So we have 36 minus 22 all over 7. That's 14 over 7, which reduces to 2. Next, to get the equation of a secant line, it's good to use point-slope form on this. So y minus y1 equals m times x minus x1. The slope is just going to be this 2 here that we just found. And for x1 and y1, we can use either endpoint here. So we either plug in negative 3 and get the y value out of that, or plug in 4 and get the y value out of that. If we plug in negative 3, we saw that that was 22. So at the point negative 3 comma 22, we can write y minus 22 equals our slope of 2 times x minus negative 3, or x plus 3. And we could also use the point 4 comma 36 if we wanted to. That would give us y minus 36 equals 2 times x minus 4. For this problem, we're using the function 2x squared plus 4, and we're asked to write an expression for the slope of a tangent line at x equals 5. So if you want the slope of a tangent line, you're looking for the instantaneous rate of change, or the derivative. So that's going to be using this limit formula here. Limit as x approaches 0 of f of x plus h minus f of x over h. Basic idea is you're finding the slope as the distance between 2 points, which we call h, becomes infinitely small. So our x value that we're plugging in this case, they gave us an x value, so we can plug 5 in for this x. So we've got 5 plus h and 5. And the actual function itself just squares things, multiplies by 2, and adds 4. So we're going to be having 2 times 5 plus h squared plus 4, because that's in the formula for f. And then we're just going to be subtracting 2 times 5 squared plus 4, all in a big parentheses. And this gives us an expression that we could eventually evaluate to find the slope of the tangent line. Now, for the next part of the question, they want us to find the equation of the tangent line through x equals 5 if the limit in this part here, part A, evaluates to 20. So for this, we're going to use point slope, y minus y1 equals m times x minus x1. We'll start with the point here. We have the x value 5. Plugging that into the function for a y value, we've got 2 times 25 plus 4, so 54. And then we also have the slope that they just gave us of 20. So plugging all that in, we've got y minus 54 equals 20 times x minus 5. And now finally, the equation of the normal line through x equals 5, not negative 2, 5, just to keep it consistent with this. It's actually going to be the same as the slope of the tangent line, except that it's perpendicular. Normal lines are perpendicular to tangent lines. So that means the slope is going to be the opposite reciprocal of 20. So we still have y minus 54. We're still going to have x minus 5 in a minute. The slope now is going to be negative 1 over 20. And then x minus 5 is the same, and there's the equation of your normal line.